Okay, so let's go. Okay, so what we're going to do is we're going to calculate psi 1 decaying into nu 1 plus psi 2 plus nu bar 2. Okay, so already you can see just from the kinematics that these guys are massless, so no problem. Anything that's massive can decay anything into massless particles, no problem with that. But because psi 1 and psi 2 are both massive, so therefore it has to be the case that m1 better be greater than m2. Otherwise this decay is forbidden, right? You can't, the electron cannot decay into a muon if everybody else is massless. It will violate special relativity, right? It will violate special relativity. But the muon can decay in principle into the electron, but we won't talk about that process. We're talking about now the toy model for quark decay. So this is the constraint that we have. But otherwise, the Feynman rule we have already done before, right? So I think I won't actually, because I don't want to take up too much time. So I'm going to go ahead and write down the amplitude and then tell you some of the, just sketch what are the subtle points here, because the integral here, the problem with this, the issue with this problem is that the integral over the kinematics is a bit messy. So let me at least point out what it is. So anyway, so let me just draw the diagram first. Okay, so here I am letting my psi have momentum k, but of course I'm going to work in the rest frame, and then later on I'm going to write down how the amplitude is going to be related to the decay rate. So let me write this down first. So I'm going to always choose to work in the rest frame, which means that this is just nothing but the mass of the first fermion with zero spatial momentum. Okay, that's just easier. So we're going to do that. And then of course we have 3 particles coming out. So now there's some non-trivial business going on. And so what we're going to do is we're going to call the psi 2 p and news q. Okay, so psi 2. So this is going to decay into psi 2, this is psi 1, and then I'm going to, in my notes I call it P2 with spin 2 prime, and then we have the neutrinos, so-called neutrinos, not really, S1 and S1Q1, and then you have S2Q2. That's why I put a prime on this P on the psi 2. Okay, so this is nu 2 bar, and this is nu 1. Okay. Remember, we have to have fermion number conservation. Right? We have one incoming fermion is decaying into a whole 3 of them. So we must have an anti fermion pair to cancel out each other in terms of the fermion number, otherwise it will violate fermion number. But otherwise that's the kinematics. And so I claim the following, that if you write down the amplitude, which I won't do for you, but the amplitude is going to look like the following. It's going to end up being, let me just write down the form of the square. It will be g squared over m squared. Okay. You see, you only need 1 power of this, constrained strictly because of kinematics, right? There's no quantum field theory here. This is just kinematics. You have incoming, shoot them head on, and then the outgoing will have to sum to zero in the spatial momentum, and then the E's are just fixed by energy conservation. Therefore, you can work out these dot products. Okay, so again, I think I'm going to skip over because it's not terribly difficult. It's just very messy, and what you will discover is the following. Okay, so let me write that down, and then we will then plug it into the cross-section formula. So this guy, let me write down something and then see whether the camera can see it, because can I see it? Can you see something? Can you see this one?
No.
No.
A little bit.
Okay. Okay. Let me do it over here then. I think here is okay, right? So
Yes.
yeah, so let's do it here. So let me erase this so that it's not so cluttered, because anyway it's part of the same calculation, right? So okay, so this remember is my amplitude. Did I lose my I? I must have lost an I here, right? Oh no, sorry, I squared it. So squared averaged, right? And now let me continue over here and tell you what the answer is, using these kinematics configuration. And it will look like the following. It will be 8 E4 over now 16.
It's also not visible to the camera.
Oh, here.
It's visible.
So from here.
Yes.
Oh, that's funny. I thought I moved. Maybe I accidentally rotated it. But from here on, right?
Yes.
Okay, good. Thank you. Plus, so it's yeah. Let me just tell you the answer. E to the 4. There's some algebra that you can go through, but it's e to the 4, 1 plus m mu over energy squared plus 1 minus m mu over energy squared, whole thing multiplied by k hat dot z hat squared. Okay, so what this is telling you that is that even after averaging and summing over the outgoing spins and summing over the initial spins, you still have an angular dependence. Okay, so what it's telling you is you collide electrons together, electron positrons together, and you ask what's the probability that you get a pair of muons and anti-muons coming out like that. It will turn out that this answer depends on the angle. Okay, that's what we're seeing here. Right, so this dot product here tells you that it now depends on the angle between k hat. So let's in fact do this. So this is in fact theta, right? So theta is cosine theta is in fact k hat dotted into z hat, right? So z hat is here. If k hat is this way, minus k hat is that way. So it depends on this angle. And that's also another signature that particle experimentalists do. Right? They usually, when spin is involved, you look for the angular distribution of the outgoing particles. So just now I said you count particles, but the other thing you do is you count particles, but as a function of angles, which is why when you look at the, for example, when the LEC, there are layers upon layers to their detector, right? And different kinds of layers. In fact, there's what calorimeter. There's usually I think the inner layer is silicon SVT, right? Silicon vertex tracker. I'm getting rusty now, but used to work in this heavy ion collision stuff. So I know they are very similar, right? Layers, silicon wafers, and then you have this what TPC and anyway. So layers, depending on what you want to measure and how accurately you want to measure. But you will try to wrap the whole collision area with your detector so that to get as much of the 4 pi stir radian as possible, right? Because of this, right? Because you do get this angle dependence in your amplitude. You want to see, does the theory match the observed results? Okay. Yeah, in fact, Pascal, I should mention, Pascal and Schroeder actually goes on to, because this is your first cross-section calculation, they go on to do the polarized cross-section, right? So if you're interested, you can actually read through that section. They do it in more detail, and you find that there are different signs showing up depending on whether you have, left-handed versus right-handed incoming particles, and and so on. But I just want to show you the final answer so that so that it's simpler. The other thing to say is that we know the cross-section, the amplitude you can see is dimensionless. So even if you didn't know what the final answer looks exactly like, you can predict just from the kinematics that it has to scale by the ratio of these mass scales, right? There's no other mass scale. They set the mass of the electron to 0, so that's not going to enter. And so therefore there's only a center of mass energy because we're chosen to work in the center of mass frame. So there's only one E and there's only one mass. So not surprisingly, you see that the answer just comes up purely in terms of this mass ratio. So this is something important when you say you invent a new theory or someone hands you a theory. That's the thing you want to think about if you're an experimentalist. What are the scales in the problem? How is the answer going to scale with the scales in the theory? And therefore, is it detectable or not? Right. So suppose the mass of the muon is very, very large. Then you see you want a large number for this guy, right? So it means that firstly you want this to be large enough because you want to be able to produce the muon in the first place. But you can see that at higher and higher, I guess we should integrate over the mass first, integrate over the angles first. But we can see that at larger and larger energies, that those terms will drop out. Right? Anyway, let's do the angular integration before we talk about that. I think I jumped the gun a little bit. So this, remember, again, this is the amplitude only. So in fact, averaged and summed over spins. So let me now erase the rest so that I can now write down the, oops, no, that was PE going in. Yeah, I just want to keep that picture in mind. But let me erase this rest and then I'll write down the cross-section formula. I think this is okay. Anyway, it's all in my notes, right? And also this part is, in particular, is all in Pascal and Schroeder, except possibly with a different notation because I worked it out. I tried hard to work it out myself just to make sure I know what I'm talking about. Okay, so let's press on. So remember, d sigma d omega, in this case, is just going to turn out to be the square of the amplitude. Let me just write down the general formula. S in this case should not have a symmetry factor because I do have an 8e squared. Let's see. It's probably because of the, yeah, okay. So anyway, so let me write it down first. It's m squared, now with the average, and then there's a symmetry factor, which I believe is 1 in this case because the muons and the anti-muons are not the same particle. and then divided by square root of the incoming particles, in this case PE dot PE bar squared, minus ME squared. But remember, we've set this to 0. So we're going to ignore that, but there is a 1/4. Okay, so 1/4 times the phase space measure. Okay, so can you still see do you know if the camera?
Yes.
Okay, good. And then now we have to integrate over the outgoing guys. Okay, so let me write it down as d3p mu 2 pi q 1/2e, and then d3p mu bar over 2 pi q 1/2e. Okay. Remember, we're working in a single mass frame, so all I've done is just I have in fact
Do you have delta function?
thank you. Yes, I do. Thank you. I'm just slightly confused by my own. Just give me 1 minute. Yes, thank you. So times 2 pi 4, and then you have both delta function in terms of energy, which is 2e minus the outgoing guys. Uh, 2e mu bar. So if you don't integrate it, there's e mu, right? If you don't integrate it yet, I'm going to integrate it, and then times the three-dimensional guys, the spatial guys, I mean, which will be 0, and then p, it will be p mu plus p mu bar, right? Because we're working in a center of mass frame, so center of momentum frame. Therefore, it's just the outgoing particles momentum. There's no incoming because the sum is 0 already. Okay. And so, as you may guess, we can now integrate over these guys, right? So you see, this is now, if you keep track of the powers of infinitesimal, is d6 sigma. d6 because d6. I'm sorry, I keep messing this up. So d6 sigma. Sorry, I didn't mean to write d omega yet. D omega comes from the angular portions of the momentum, right? So I'm sorry, I just wrote that too fast. But as you can guess, now we're going to integrate over as many variables as we can, and we will discover that there will in fact eventually be only the angular dependence left, because you see we have so many delta functions, right? You see you can count. There's six integrals to do in principle, and there are 4 delta functions. So we should expect that at least 2 of these, only 2 will remain, right? And the 2 will in fact turn out to be omega, the angle of exactly the angular solid angle that shows up in d sigma d omega. So in fact, let's just go ahead and do it. Right? So what do? We say that we integrate over first we integrate over the spatial momentum, either p mu or p mu bar, and that's what we call k. Yeah, so which then we call p minus, I believe, let's stick to this, we call it minus k, and then so then you get d 3 sigma, right? Because now you have integrated over one of the momentums, And what you will discover is then you can convert it into the following. That's the first step. The second step is remember that E, of course, is square root of k squared plus m mu squared. Right? I'm talking about outgoing energy. So dE is therefore let's do it. What square root? Bring down the power 1/2, and then bring -1, and then dk 2 dkk. Yeah? And then the 2's cancel, so therefore dk times k divided by this guy's energy is nothing but dE. In other words, E dE is in fact nothing but dkk. Okay, so this is just a change of variables that you want to do. And so again, integrating over the spatial momentum, converting the radial component of your momentum into energy, then allows you to integrate over the energy. Right? So this means that this is the radial integral in momentum space, in p space, is energy integral. Why do we do that? Because we have a delta function in energy. Okay, so and then what you end up with is the following. So again, I'm telling you what the steps are, but again, to save the time, I'm just going to tell you what you end up with is in fact d2 sigma. Yeah, okay, now I can erase this, yeah, because I'm going to write it down. Now it will be d2 sigma. Right, so down to integrate over this, you get d3 sigma. Integrate one more time, you get d2 sigma. And then you get the following. You get e to the 4 over 16e squared. Now E is just the center of mass energy that you set up your conversion in. And then you get 1 plus m mu over E squared plus 1 minus m mu over E squared times k hat dot z hat squared, and then the whole thing is multiplied by d2k hat. Okay, remember this step means I have taken d3k vector into d2k hat times dkk dk involving the radial component, and then I change my variables from dk to de, and I claim this is what I have left. Okay, and so then you have the following. You get d2k hat, the angular part, divided by 2 pi squared, and then you have, if you pull out the e, you get 1/4 square root of 1 minus m mu over E squared. Okay? So again, the kinematics will give you the angular, the per angle that we expect. Okay? In fact, and so therefore, we can now move this guy over here and call this the differential cross section. Okay? So differential cross section is now basically d2 sigma d omega, which is just d2 sigma divided by d2k hat. Okay, so I won't write it out again. I'm just saying that just take this guy, move it over to the denominator, and the rest of this guy is now the cross section per solid angle. And this already is a measurable quantity. Right? So you can go out, you can build your detector, you can put your E plus E minus collider. That's what people do at Stanford, basically SMAC, the national lab. I think it's still running. So you collide beams of positrons with beams of electrons, and it's a linear collider, right? So it's just head on a straight line. And again, in principle, if you build your detector around that collision point at leading order at high energies, that's what you should find. This angular dependence. So actually, I'm going to skip over the final integration because it's just integration over solid angle. So maybe I'll just say, right. So k hat dot z hat. Right, I purposely call it z hat because that's the z direction. So k hat dot in the z hat is nothing but cosine theta, and remember omega itself. If it involves integration over the azimuthal angle, which you discover here is actually independent of phi, right? It's because basically you have a azimuthal symmetry. You collide the particles together like that, so it's azimuthally symmetric. Doesn't matter how you rotate the system. But there is now a theta dependence, so there'll be a d cosine theta. Okay, so and this integral will be from -1 to 1. Cosine runs from -1 to 1. So when you integrate over this expression over here, the only thing you really need to worry about is this guy. There's a cosine squared here, but it's a polynomial, so there's no problem. D cosine dc c squared. The rest is just constant, right? So cosine from -1 to 1 is just 2. And then multiplied by this phi is 4 pi. So integral over all these guys are just 4 pi, except, sorry, this guy, these two guys are just 4 pi, but this guy will involve 2 pi times integral of c squared with respect to c from -1 to 1. Anyway, I won't complete that step because it's nothing terribly difficult. Right? Okay, so okay, so now I want to at least sketch. So give me a little bit more, at least half an hour. Okay, are you in a hurry somewhere?
No.
Okay, yeah. So give me another. So at least now you can see the kinematics involved. In other words, writing down the amplitude is only the beginning. In fact, you've got to plug in the cross-section formula, you've got to do the integrals and so on. But so now, let's at least sketch what happens with the decay calculation. And in fact, you're going to do it in your homework. I don't think there's a cross-section calculation. In your final homework, you're going to have a one-loop 5-4 theory calculation, but actually it's just a quantum mechanics problem. But you're going to do it to one loop. And then for the amplitude calculation, you're going to do a decay. And it's actually very similar to what I'm about to do. Just slightly more complicated. I think I just added some fudge factors just to force you to step through the relevant calculations without just copying.
The one loop problem means the Euclidean pattern.
Right. Yeah, that's a 5-4 1D one loop calculation. By the way, that one again, actually I've already drawn the diagram for you in class, right? So all you have to do is figure out how to do this calculation in one dimension. And the reason why I dare to give it to you is because it's a finite calculation, right? Not unlike in
for the Euclidean pattern.
it's finite because you're on one dimension. I think in high dimensions you will probably diverge as well. You can do a power counting, but anyway, yeah. So I just want to give you guys experience doing a one loop calculation because in itself not that crazy. It's the divergence that makes it a bit crazy. Anyway, so now we're going to do a decay of a fermion. Okay, and this is a little bit tricky, so I'm going to tricky in the sense that it's quite messy. For example, let me just say that this is the toy problem for quark decay. So for example, neutrons decay into protons. So neutron decays into protons. Right, so this is neutral, so I need an electron. But once I produce an electron, I need to produce an electron neutrino, anti-electron neutrino. Right? Otherwise, fermion number is not conserved. Right? So I have to, these guys have to cancel, and then this fermion becomes this fermion. So this is a toy, I should say, toy model for this process. And even if you do use the electroweight theory to do this calculation, you're not going to get a nice answer because the quark is sitting inside a neutron, which is a bound state, right? Hadronic bound state. So because of that, there will always be contamination. It's just actually shouldn't call it contamination. It's just physics, right? So just quantum chromodynamics effects that you can't run away from because the quark is it never appears as a standalone object. It always is bound to the neutron itself. So even this is a weak interaction process, but and so you can make it a good ballpark estimate. I forgot now the numbers. I think it comes within that kind of 10% or 15%, something like that. Griffiths does this actually in his book. And probably Peskin and Schroeder as well, but sometimes Griffiths actually explains things a little bit more cleanly. Anyway, so either book I think does it, and what we're going to do is actually I think just a much simpler model of this. So let's go. Right. So our Lagrangian is now the following: there are two species of size. And there are also two species of nu for neutrino, right? Again, it's a toy model, but here we go, right? So psi I, capital I is the label of the fermions, partial slash, now there's no photon, it's just a fermion, minus mi, psi I, and then I'm going to make my neutrinos massless. Okay, so it's no longer true. Long time ago, particle physicists thought that maybe neutrinos are massless, but no longer. Okay, they probably have mass because they oscillate, and the simplest explanation for that is that they have mass. They suddenly oscillate, and so now it comes down to what are the absolute mass scales of these guys. So so let me write that down. So now we allow them, so these are just the kinetic terms, which I hope by now is familiar. So we have 4 fermions in total, 2 psi's and then 2 neutrinos. And this is to like I said, is to mimic what's happening here. Right here, we need 4 species of fermions. So that's supposed to be the toy model for that. Anyway, so we have psi bar 1, nu 1, and then psi bar, nu 2 bar psi 2. Okay? And then of course this thing is not Hermitian. So I need to add its Hermitian conjugate. So I'm just going to write down Hermitian conjugate. Right? For example, there's no nu bar 1 psi 1, as you can see. So we need to add this Hermitian conjugate. But this is okay. So this is what we're going to mean by the average and the sum of this guy. Okay? And so let's in fact do it for our amplitude over here. So you do this again for processes that you don't care about measuring spins, right? So you sum over all the possible incoming states, incoming spins, and you average over the outgoing ones. Okay. Anyway, so here we go. So in this case, what we have is 1/4, and then you have e to the 4. E to the 4, by the way, is alpha squared. Alpha is actually e over 4 pi, so it's related to alpha squared. But anyway, I'm going to leave it as e. E to the 4th power and q to the 4th power as well, which means q, the square of q squared, right? And then what we have here is the sum of all the spins. And so what we have the following. We have the square. We have the square of each individual guy. So let's write it out. Right. So firstly, we have this guy here. But then if you write out, okay. So let's write it out. U, P mu, U bar, P mu S mu, and then gamma alpha, V P mu bar, S mu bar, and then if you write out the complex conjugate of this, remember we have a square, absolute value square. What you discover is that the identity you're going to prove in the homework is going to be very important, which is that the dagger of this guy is just, in fact, itself, is Hermitian, basically. But because you are taking the dagger, you've got to swap the V and the U, so this becomes in fact V bar, P mu as mu bar, sorry, P mu bar as mu bar, and then you get gamma alpha prime, U S mu P mu. Okay, and then I need to see whether I think I'm out of the picture. Am I right? Yeah, I'm out of the picture. Let's see. If I draw a horizontal line, can I see it? Nope. Okay, so let me do it over here. Too small a space. My board is too small. Okay, so maybe the camera is too near. I think that's it. Yeah, so right. So let me do it again. Right. So m squared is 1/4 sum over spins of this fellow squared. So it is e to the 4th power over q to the 4th power times u bar s mu p mu gamma alpha v p mu bar s mu bar, and then like I said, there's a gamma 0 here, gamma alpha here, and that's Hermitian. But when you take the complex conjugate, you swap the u and the v, so you now get v bar s mu bar p mu bar. This guy is going to be contracted with the other, is counterpart over there. So this, we need to cook up a new index, alpha prime, and then you get u p mu s mu. Okay? So the spins are the same. The momentum are the same, but then these index I have to cook up a new one. Anyway, let me write that down and then we will discuss what happens. Basically, this is where you need to use your spin sum formula. Okay, and so, but let me write down the other term first. So multiplied by V bar, SE bar, PE bar, gamma alpha, U, PE, SE. And then its complex conjugate, which would be U bar, SE, PE, gamma alpha prime. Remember, this was contracted with this, so when I take the complex conjugate, its counterpart is going to be contracted with this counterpart. Right? So this, if this is alpha prime, this would be alpha prime. And then finally, V, PE bar, SE bar. Okay. Okay, so now, yes, so now we got the sum of all the spins. And so let me make more space. And since I have written this down, I'm going to erase this. Or rather, since I've squared it, I'm going to erase that part. And I guess I should leave this line here, just to remind myself the limited space I have. Okay, so essentially we have to recall that the sum over the spins, doesn't matter what the momentum is, but they have to be the same. U bar, sum over the spins, in fact give you P slash plus N. Okay, but of course it's the N associated with this guy, whatever the fermion is. So we have to keep track, right? If it's the electron, it's the electron mass. If it's the muon, we need to write down the muon mass. So otherwise we'll be in trouble. Okay, and so I'm going to, and then also likewise, if you sum over the spins for the V's, I believe you will get a minus. I believe. Yeah. Okay, so you get V. So what I mean by that is if it's U. PS V bar PS sum over the spins, you get P slash minus N. Okay, and let's use these guys. I think one of them we proved in class, the other one or maybe in my notes, and then the other one was supposed to be a homework problem. Right? So in my notes I proved it, and Paskin and Schroeder also does it. So what happens then is the sum over the spins now becomes the following. 1/4, let's pull out the constants, right? So e to the 4 over 4q squared. And then now if you sum over the spins, this guy will give you, you can see, P mu bar slash minus m mu, okay, this factor here. And then you have a gamma alpha prime, okay? And then the funny thing is that now this guy is going to give you a matrix as well. But this is now sandwiched between this n and this n. So if you work out the algebra, this basically ends up being a trace, okay? A matrix trace, okay? But because it's a trace, doesn't matter whether you put, this will become a P slash plus M. But it doesn't matter whether you put this to the left or to the right. Okay, so this again, this factor and this factor will give you P slash mu minus M mu. But it is a trace because this factor is here and this factor is here, and it sandwiches these guys over here. Okay. And then likewise, something like that will happen here. So multiplied by, it's going to be a trace, but let's first do this guy here, right? So this is now PE slash plus M E. Okay. This sum. And then I have my gamma alpha prime, and then when we come to here, that's where we end up with a trace. Again, it's sandwiching these matrices between them, but component by component, when you sum over the spin, is actually equal to the component of PE bar slash minus ME, and again it's a trace. So, so what we're going to do is we're going to assume that we have in fact smashed these guys with large enough energies. Okay, so we're going to assume that collision takes place at very large center of mass energies, much larger than ME, much larger than the mass of the electron. And remember, we have to at least do it at twice the mass of the muon, because otherwise you won't produce the muon at all, right? It's kinematically forbidden. It's not even about quantum field theory. It's just not possible by special relativity to produce something that is too massive if you don't have enough energy. So it's a reasonable approximation, right? You have to do it at 200 times, so may as well pump it up even more. Make sure that this is basically zero, right? So that's all I want to say. That we are going to, just to simplify the analysis, we're going to set this to zero, okay? Just to make it easier. And then the next step is exactly where the gamma matrix gymnastics come in. So I'm just going to tell you the formulas again, but I can tell you where all this comes from. It just comes from the Clifford algebra of the gamma matrices. So especially if you don't like math, it's perfectly fine to just apply them. Right? You know that these are well-established formulas, but let me just tell you. I'll give you a simple example, for example. So remember that what we're doing here is we're going to sum over, or rather trace over the product of gamma matrices. For example, we're going to have something like that. Gamma, trace of gamma alpha. What is this? This is over zero. Okay. What is trace of gamma alpha, gamma beta, for example? Well, yeah, so what you do is you try to write this as a anti-commutator, because the trace is doesn't care about order. Trace of AB is the trace of BA. Okay, so what you can do is you can write this as trace of gamma alpha times gamma beta plus gamma beta plus gamma alpha. Anyway, with the swap, with the indices swap, and then you divide by 2. So this is basically 1/2 gamma alpha, gamma beta, anti-commutator. But this is where you can use the Clifford algebra of the gamma matrices. And this will give you basically 1/2 times 2 times the trace of the identity times the eta alpha beta. Okay, so this again, this steps just require the Clifford algebra. Gamma alpha anti-commutator with gamma beta is 2 eta alpha beta. Okay, and so the trace of the identity is just 4, and this is cancels out, and so you just have 4 eta alpha beta. So basically, you can keep going to get the trace of 3 gamma matrices, 4, and so on. But I claim they all come from the anti-commutation properties of gamma. So let me just tell you what happens in general. Okay, so I've written down the 2 case. Let me just say that the odd, if you have odd number of gamma matrices, is 0. Okay, so this will generalize to all odd matrices. So trace of odd gammas is 0. Sometimes you need the 4 case. So you get trace of gamma mu, gamma nu, gamma alpha, gamma beta. And so what you get is you get the 4 times eta mu mu, eta alpha beta, I think it's basically a contraction, minus mu alpha mu beta plus eta mu beta eta mu alpha. Okay, this is a contraction. The way to remember is you contract these two pair, you get eta, and then the other two you don't have a choice anymore. And then you just swap the indices and make sure that you put in a minus sign whenever you swap it. That's how I remember it at least. For later on, there's something called a gamma 5. Gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3, which I'll talk a bit later when we talk about decays. But there's also a rule for that. So for example, trace of gamma alpha, gamma beta, gamma 5 is 0. In fact, we can see why, right? There are 4 of these guys. 4 plus 2, no, actually, sorry. This one requires also the anti-symmetric property of it, I believe. So let me not go there. Let me just tell you it's 0. And then trace of the 4 gammas with gamma 5 will give you the Leibniz-Beta symbol. Gamma alpha, gamma beta, gamma mu, and then gamma 5 would give you minus 4 I epsilon mu alpha beta. Okay. Anyway, these formulas you can find in the back of Pascal's shoulder. So you don't really even need to copy it down if you just download the Pascal's shoulder from your library, from the library. Okay, but I do need to make sure that I keep track of these guys for now. Okay, so let's go ahead and do it. Okay, so okay, let me do it below for the moment, and then I will have to erase something eventually. So what the strategy is, let's expand it out and see what are we dealing with, right? So firstly, trace of gamma alpha, this factor here, let's expand it out, right? So you have gamma alpha, and then when you expand it out, you have p slash mu gamma alpha prime minus mu and mu gamma alpha prime, and then you have p slash mu minus and mu, and then this will give you, you just have to keep going, trace of gamma alpha p slash mu gamma alpha prime p slash mu, and then minus, let me keep going, gamma alpha.
The first is mu bar.
Nah,
The first P slash is mu bar.
this one mu bar, thank you.
So
mu
the
bar.
first M is also mu
This
bar.
is mu bar. Yeah, thank you. And then so now I'm here, right? Gamma alpha, and then remember m mu is just a number, but we have gamma alpha prime, and then all of it is going to be multiplied by these guys. So let me say p slash mu, right? Yeah, and now I swap my p slash mu with minus and mu. But let's see, okay, so if I do that, you have 1, 2, 3, that is 0. Okay, so because when I trace over odd number of gamma matrices, it is 0. So remember what I'm doing is I'm expanding this out, right? So instead of having p slash mu here, I will have n mu, but it will be 1, 2, 3. That's trace will be 0. And then here also 1, 2, 3. So this will be 0. But then the counterpart with m will not be. So let's do that again with m. So it will be minus will be plus gamma alpha p slash mu bar gamma alpha prime and then m mu. Okay.
The
did I
first
screw
is
up?
a mu. It's a mu product.
1, 2, 1, 2. Thank you. Yeah, like that, right? So m mu squared, in fact. Right? And so, thankfully, we now have reduced to only 2 terms. Okay? And in fact, what you will end up with is this is exactly where you have 4 gamma matrices, and that's this formula that you have here. Whereas this is just 2, right? So you get eta from here, and you get a bunch of etas here. So I think this part I'm going to skip over because it's just contraction, right? So there's a similar calculation you do over here, and so I'm just going to tell you what the answer is because there's a lot of algebra there which I just think is not terribly useful to go through. Yeah, so what I have in my notes, together with ME being 0, is the following. Right, okay, so what I get is the following. This is equals to 8 e to the 4, and you're welcome to check it. I think this does check against Pesky and Schroeder because this is actually from there, although I did do it myself. And then this will be, maybe even the notation is a bit different, m mu squared pe dot pe bar. This is now the 4 product, right? So there's a contraction using eta mu nu here. It's not a ordinary dot product. Plus PE dotted into P mu, and then there's a PE bar dotted into P mu bar. They're just 4 momentum, so basically you just end up dotting it with each other, and then finally you have PE bar dotted into P mu, and then PE dotted into P mu bar, as you might suspect, right? So right. So this is where. So again, remember this is. Did I say? I think I erased it. So this is with ME set to 0. Okay, which basically amounts to assuming that the center of mass scattering, the center of energy is very large, so that all these momentum are very large. Right? These are all dimension-full quantities. So if you write out the mass terms, and you compare with these terms, I guarantee they'll be small. The mass terms will be small. So this is where we make a further simplification by choosing the right coordinate system, right? So you choose the right coordinate system by saying that let's now put the incoming particles on a straight line, which is z. So let's do that. Okay, so I'm going to erase this part. I think I'm going to save that for the moment, just to make sure I can continue writing the same thing. Okay, so now the setup is as follows, right? So So let's say that z hat is in this direction. So the incoming electron, remember we're taking electrons and positrons and we're going to produce muons and anti-muons. So this guy would now be basically the energy of the electron and then one z hat. Okay, so in other words, it has positive energy E, capital EE, and then it's moving, the momentum is spatial momentum is moving along the z direction. And we're going to work in the center of mass frame. Okay, so what does that mean? It means that, well, if this thing is moving in the positive z direction, then the anti-muon better be moving in the opposite direction. So it will be just E times 1 minus z hat. Okay, so that the sum of the spatial momentum is 0. And therefore, by conservation of momentum, you know that the outgoing guys also have to conserve momentum, right? The sum of the incoming guys have 0 momentum, spatial momentum. So the sum of the outgoing guys, no matter how they go, also have to obey momentum conservation. So P mu has to be equals to, in my notes I call it E mu, and then 1 k hat, sorry, k vector, sorry, no, because I don't, this is, I should mention, this is true because I assume that the electron is massless, right? Of course the electron is not massless, but you can see P squared and P bar squared are all 0 in the 4 vector sense. E squared minus E squared is 0. But in the mu1 case, I'm not going to assume that it is massless. In fact, it is not massless. So therefore, I need to be a little bit careful. It must be therefore equals to E, and then minus K vector. I think I call this class K. And then therefore, P mu bar, again, to conserve momentum, must be minus K. In fact, of course, energy is conserved, right? So I don't need to call this EE. It's just E. Right? So that's what that is. Conservation, yeah. So always remember the kinematics is important as well. If you choose the right orientation, the variables do simplify. Right? So as you can see, at least in this massless limit, things do work out. So what's going to happen is, for example, you can think of, for example, what is Q? Oops. Q is, Q squared, I mean, is P mu plus P mu bar squared by conservation of momentum. And of course, it's also equals to PE plus PE bar squared, right? PE plus PE bar squared. That is the that is in fact the kinematics of this problem, which again I erased the diagram already, but remember it goes like this: PE bar. When you calculate your Feynman diagrams, make sure you have many pieces of paper, right? Because you can see it's very messy, and then you want to keep track of your kinematics and so on. So it's very messy. It's not really, once you know the rules, it's not super difficult, but it is very messy. Right, and that's why, like I said, you need many pieces of paper just to keep track of what's going on. P mu and P mu bar. Okay, and so this is Q, remember. But like I said, the kinematics tell you that the Q, of course, is just either the sum of this pair of that